Hey everyone, I'm Ben, and today I'm going to be talking about building a real-time video processor with Swift and Metal. Briefly about me, I'm the development half of the team that builds a couple third-party camera apps. One of them is Spectre, which is used for generating computational long exposures. And the other is Halide, which is a manual camera app. Both apps use a lot of real-time video, if only to show the viewfinder. But in the case of Halide, we're using it to create our own version of the portrait effect that you might see in the first-party camera app, where we're creating a beautiful blurred background in real time for the portrait preview. So in today's talk, I'm going to be talking about the overall architecture in building a real-time renderer. We'll touch on some of the performance considerations as you're designing it, and some of the nuances when working with image data. I'm going to be using that portrait effect as an example project because it's actually pulling in two video sources. One is color data that's coming off the camera in real time, and the other is depth data on devices that support real-time depth. While we're generating that image, I'm blurring the background and compositing the two images together, the sharp image and the blurred image, to recreate that effect that you see in the first-party camera app. So we have a lot to cover, so we'll just dive right in and talk a little bit about architecture. So I'm going to spare you all going line by line through Apple's documentation on how to get camera frames from the camera. And I'm going to talk about things at a bit of a higher level. Okay, so you hook into AV Foundation and you tell it, please send me video frames as they arrive off the camera system. And that's where things get interesting. So the system will deliver frames to your app at 30 or 60 times per second. Your processor will likely, if it's doing something interesting, have to update its internal state. If you're building your own animations, you might be ticking the animation and progressing it along or what have you. And then your app will issue commands to the GPU to render the content. Much of your work is going to be done in Swift on the CPU side, such as updating its internal state and telling the GPU to execute commands. And then you're going to be executing your own shaders, which are written in a subset of C++, which Apple calls Metal. And that's going to be executed on the GPU. Shaders are these tiny programs that are executed on hundreds of threads in parallel. You could think of shaders as running once per pixel on screen, and they're designed for massive parallelization. Now, if you've dabbled at all in game programming, this flow should seem very familiar. So you're going to be processing, in a game, you're processing 30 or 60 times per second, an animation timer will fire, and you'll process input, update your game state, and then issue commands to the GPU. If you want to learn how to build a real-time video processor, just go study game programming, and you're probably 80% of the way there. So that said, you're going to be actually using the same hardware that was originally designed to build 3D games. And as such, I'm going to use that as an example to show you some of its power. But there are really two tools at your disposal that leverage the GPU. The first is the 3D rendering pipeline, which makes it easy to render 3D geometry. And then more recently, there's been a movement toward a compute pipeline, which for more general purpose GPU programming, basically Bitcoin mining. You could use it to write any massively parallelizable solution to a problem. That said, while this compute pipeline may be a little easier to understand, you still need to understand the 3D pipeline because that's what you're going to have to use to render content on screen using Metal on iOS. So let's dive into some scary parts about 3D rendering, but I swear it's a lot simpler than what I'm going to dive into in a second here. Okay, so in a game, as part of your render loop, you're going to have a bunch of entities that you're going to want to render on screen, such as enemies, player characters, the background. So every time you reach the render phase, your engine will loop through all of the 3D models that need to be rendered on screen. And for each 3D model, it tells the GPU, configure yourself to run these shaders, and then execute the draw call, and then move on to the next object. So you could be rendering over hundreds of separate 3D models on screen, and each model could have thousands or tens of thousands of vertices that make up that 3D model. Okay. Fortunately, For rendering video, you have the most boring 3D game ever, where you're just rendering a square on screen. You don't have any complex texture effects or cool lighting. You just render the frame that's coming off the camera. It's probably the most gentle introduction to 3D rendering you can ask for. So to render the content, there are two phases. This isn't as relevant to you, but it's the first pass you can make over the vertices that you're passing to the GPU. And in our case, we're not doing anything interesting, but if you were to render a 3D model, your vertex pass or your vertex shader would perform a bunch of transformations on this 3D data and project it onto a 2D plane relative to the camera. And you don't have to worry about virtually any of that, but you have to go through this process to get to the interesting bit, which is known as a fragment shader. A fragment shader is used for actually rendering the 3D surface that makes up your model. Okay, this is where you would code something to generate like a flat surface or a shiny surface, or more importantly, at this fragment shader pass, you can read and write to texture maps. You can think of a texture as like a super bitmap, okay? But it's much more powerful than a regular, just a 2D image data. So a texture is a term you'll hear when working with the GPU, and it allows you to read and write 2D data, but more importantly, you can represent your data in all sorts of powerful ways. You can access hardware-accelerated operations like filtering, which is being operated on your GPU on these texture processing units. So it's a very, very powerful affordance available to unlock some of the power on your GPU. Cool. So I've talked a lot about theory, but here's a very simplified example of what you do on Swift to set up your rendering. Okay, in Swift, you would start describing the render pass you're about to make. So you tell it, I want to execute this simple vertex and simple fragment shader as part of this render pass. And you'd probably do this when you're first launching your app, and then you store this description later. Later, as the frames are arriving in the system, you say, load the render state that I described earlier. Here's the data that I want you to execute with these functions as parameters, and go to town, execute the render pass. Okay? And this is the actual shader code that gets run. There will not be a test on this, but this is the hello world of rendering a 2D image. The middle part, simple vertex, is the vertex shader that doesn't do anything. It basically takes the vertices that we're passing to the shaders, and we're just shuffling them down and not modifying them. And then that fragment shader, all that it's doing is it's reading the texture data that I pass to it at the coordinate on screen and renders it to that 2D square that we described earlier. And most importantly, to pass data between vertices or to pass data from Swift to your shaders, you're probably going to be using C-structs. And the data layout is very, very important. And you'll be tagging it, all of this content very often with that double bracket syntax, which annotates the compiler. This is where you hook in this parameter that I passed you in Swift. Is going to be slotted into this parameter in my shader. Cool. So that said, that's a bunch of boilerplate, and you probably don't need to use most of the tools available in the 3D pipeline. So with a compute shader, you can ignore all that vertex stuff and just read and write directly to coordinates inside of your texture map. Okay. Instead of that 3D pipeline, you just think of your image as a grid with different slots in it, and you just tell the system, execute this compute shader on this grid and do whatever you want. It doesn't even have to be image data. Again, it could be crypto mining if you want, but it's a very general purpose approach. So when would you want to use each tool? Well, compute shaders they feel more technically correct, but one, you still need to know the 3D pipeline to render stuff on screen, and two, if you were to build something like UIKit, where you have a bunch of different images that might be overlapping, it's nice that the GPU can actually know when different surfaces are occluding each other and discard that geometry for you. So one of the things you want to avoid is known as overdraw, where you do a bunch of computation on something that never actually gets displayed on screen. And GPUs are designed to optimize this, where it'll actually throw away geometry and not run the shaders, which will free up resources. Cool. So one last thing I want to touch on, which will segue to our talk about performance. All of these operations are running asynchronously. Once you get to the CPU and you run the GPU command, it's non-blocking. So potentially several milliseconds after your code runs, it will then be displayed on screen. And it's up to you to be always passing things down through this pipeline and never blocking your code. The other thing to understand is that there are very limited resources when you're working with graphics. If you just do the math on the resolution of your iPhone screen, like think of how much memory goes into a full resolution bitmap. A 12 megapixel image that would come off the camera, full resolution, is 12.5 megapixels with 4 color channels, which means 48 megabytes of memory per frame. That's a lot of memory. So fortunately, you don't actually render full 12 megapixels on screen, but you still need to be aware of resources. And what I would hope, be doing is creating a pool of resources. And then constantly, as each frame is coming in, you pull a texture off of your pool. You do whatever interesting bits you want to do with it. And then after your frame has been rendered on screen, the resource gets recycled back into it, similar to UI table view rendering, where you're always recycling resources for what's actually being displayed. Okay? In all of our apps, we're using what's known as triple buffering, which means we have basically 3 times the amount of resources we need, which gives us a little leeway. If one of the frames lags, we don't start dropping frames. We always have a little headroom to pull off a new resource as we're pushing it down through the pipeline. So that brings us to our next section, which is performance. So in a perfect world, I would just be taking this data in from the camera, executing the shaders, and then displaying it on screen. Well, turns out with depth data, you think that you're going to get the image in the middle, which represents this flower with all of the full Z depth. In fact, if you rendered it on screen, you'd see something on the right. And that's because depth data is actually delivered in units of meters. It's not clamped between 0 and 1. So we basically need to pre-process the depth data to clamp it within a usable range before we hand it off to the shaders to render it. So that's just one example in Halide. A few years ago, I did some contract work for Periscope to build their real-time drawing feature where you could draw on your periscopes in real time as they're being rendered. At any given time, you could be dealing with thousands of points on screen that you have to loop through with every frame to update their state, because after a few moments, the drawing disappears. So you're potentially looping through thousands of values in a very short period of time. At 30 frames a second, you have 32 milliseconds. If you're doing something with high frame rate like 60, you're looking at the same 17 milliseconds that everyone here probably knows through scrolling on UIKit. So you have a very small window to operate on a lot of data at once. So it's very similar to game programming, again. And if you were to ask a game programmer, what is the secret to performance? The last thing they would say is CPU. Not only is Moore's Law dead, but it has not been the bottleneck in game programming for quite some time. The bottleneck in most games is actually reaching out to main memory. The memory on your computer has not kept at the same pace of improvement as CPUs. The way that hardware architects have gotten around this is that your system is designed with a hierarchy of memory, where main memory is the slowest. We're not going to count a hard disk. And then there's a super, super fast bit of memory right on your CPU die, which is known as L1 cache. It is blazing fast, but they can't fit a lot of it. So it's very small. As you're pulling in data to work on the CPU, it's likely being fetched in a full line, like a batch of data, about 64 bytes at a time, so that likely you're going to operate on the full line of memory at once. And as your L1 cache gets filled up, the least recently used data gets pushed back to L2 cache, which is a little slower, but there's more of it. And as that gets filled up, it gets pushed to L3, or some systems have even L4 beyond L3, with each level of the hierarchy getting larger but slower. Now, I'm going to steal a demo from, that was created by Scott Myers, who's a very well-respected C++ programmer and has written some awesome books. And this demo is to try to illustrate the difference between memory speeds. So let's say L1 cache is about 1 second. OK, cool. Well, L2 cache is about 2.5 times that. What's L3 cache? OK, well, that's pretty bad. And main memory, you want to go get a coffee, check Twitter, come back when the data is actually fetched in there because it's still loading. So the best quote I've heard from Mike Acton, who's an advocate of data-oriented design, is that there's, especially in computer science, you're taught about the time-space complexity trade-off. Well, it turns out a lot of the speed, it actually doesn't have to do with like the memory size. Like, it has to do with just being more efficient with memory, and it turns out you're a lot faster, because if you can squeeze all of your data into, say, L1 cache, you're looking at a 40 or a 30-time improvement over having to reach out to main memory. A typical iPhone, this is as of last year, looking at just the matrix of the most used iPhones in the world, a typical iPhone has about 64 kilobytes, that's with a K, of L1 cache, 1 megabyte of L2 cache, 4 megabytes of L3 cache, and then they don't document it, but roughly 2 gigabytes of main memory. Okay. So this has some very interesting implications, and if you're interested in learning more about this, check out videos by Scott Myers or Mike Acton, who's the former engine director over at Insomniac Games. But the general idea to bleed the most performance out of the system is to arrange your data in cache-efficient structures, to use less memory, and to arrange it in ideally a straight line so that your CPU can make use of prefetching, and it can operate in a very linear fashion, or at the very least a predictable fashion, so that you're working with the CPU. You want to think of, instead of, a lot of programmers think about problems now in terms of abstractions, but really think about the transformations that are taking place in your data, and watch those 2 videos on YouTube. But let me give you a concrete example of how you would design something around data. Let's say that you're building a game like Stardew Valley, and you need to represent something like a patch of wheat that's part of your field. And you want to regularly have the wheat grow. So over the course of a frame, you might iterate the grow property for each item in your field. Now, if you were to look at the problem from an object-oriented approach, you might model it in something pristine, like you have a wheat patch object, and has a position in world space that's part of it, and it has a height field, and then you loop through all of your wheat patches, and of course, because we're OO, we send it a grow message. We wouldn't want to iterate this counter. No, we want to encapsulate it. That's terrible for performance. Typically in object-oriented languages, and especially in Objective-C, for starters, all of your objects are allocated on the heap, which means they're just in random locations, and you can't fetch them in a straight line because they're not continuous in memory. Also, Objective-C uses dynamic dispatch, which fights the instruction caching that's also part of your CPU. And more importantly, it makes you think of the problem in terms of the abstractions and the instances that make up these entities, as opposed to what your computer actually wants to operate on, which is just arrays of data. So the good news is that Swift is an awesome language for data-oriented design. And I'd say competitive with C and C++, because for starters, with operating on structs, you actually have control over the data layout. In fact, you can allocate just one array of Swift structs and just tell the CPU, go, run, and it can just zip through it in a quick line. 2, it uses static dispatch by default. So that means that you're not going to run into any of the issues with instruction caching. And just conceptually, it encourages you to use values instead of these heavyweight objects. So to contrast the 2 designs, on the left is OO, on the right is the most ideal data-oriented design. I'd say in practice, you'd still want some kind of abstraction over an array of arrays, but this would be the ideal system that your CPU wants to work on, where you could represent the data as just uint 8. Cool. Now, even if you don't go to that level of detail with working with your data, I'd love you to walk away from this talk thinking of data-oriented design, like without even thinking about assembly or any of that. Now, let me give you an example. So I mentioned blurring earlier. Now, a Gaussian blur is notoriously slow as you increase the radius, the blur radius. It performs in a time complexity of big O of n times r squared, with r being the radius. So as you get blurrier, it requires way more resources to perform. Now, there are approximations of a Gaussian blur that can give you a similar effect, and they can approach linear time. By all means, use that. But another way of looking at the problem, if you have an awesome, beautiful blur, by the way, some of the trade-offs, by the way, with different blurring algorithms is you start seeing artifacts, like with box blurs, you kind of see square looks. So you might want to still stick to a Gaussian blur, which has not particularly great performance. Well, the best solution, or a solution I've used, is you actually downscale your image to 1/4 of its size, run the Gaussian blur on that, and then upscale it with the help of hardware to the full size. On the left is a full-size blur image. On the right is the downscale blurred and then upscaled. In addition to operating on 1/4 of the number of pixels, the blur radius actually gets to be half the radius as before because it's a smaller image. And almost no users are going to be able to tell the difference, and especially in real-time rendering, when it's not the final image, it's going to come out and be written to your camera roll. So outside of graphics programming, again, you don't need to think about assembly to really understand the flow of data. So and I think Joel Spolsky has a great example of the abstraction that you get over memory when you're working with a matrix, where if you're iterating over an array of arrays in C, and you go row major versus column major, row major is actually going to be working with the CPU and allow it to prefetch. If you have a zigzag pattern on the right side where you're iterating through the first column of every row in memory, then you're going to be fighting against prefetching, and you're going to lose a lot of performance. So switching a simple loop from using column major to row major, even in a very performant system, I saw a 100 microsecond difference effectively for free. I didn't have to write a single line of assembly to get this. I just thought to myself, wait a minute, why am I not going in a straight line? Cool. So fortunately, that's the scariest thing about performance, but as long as you architect around the data and accessing it, everything's going to be okay. So now we get to the fun part. We've got an efficient rendering system, and it's now time to actually display the content on screen. So here we have this photo that we have of these flowers, and we wrote the shader, we pull out the color value for RGB, and we get red. Okay, that's weird. Now, the reason for this is that very often the data that's going to be shuffled around is in this different format. It's not RGB. It's called YUV. What is that? You can actually represent an image, not just in RGB values, but by separating it into luminance, which is the brightness value, and chromaticity, which is the color value. Okay? That V or UV refers to the position in this color chart for what the color value is. You might also hear this referenced as YCBCR. The CB means the amount of blueness, and the R means the amount of redness. So that corresponds with the different axes that are made up here. Why would you do this aside to frustrate programmers who are just getting started with graphics programming? Well, has everyone here seen this optical illusion that was floating around on Twitter? It's really cool. If not, maybe I'll put in a link up later, but this image looks like it's in color, and you might not be able to see it on the projector. But in fact, if you were to zoom in on the image, it's in grayscale, but it has these color crosses that are over the image. And this has to do with how humans perceive color. We are less sensitive to color shifts than we are to luminosity shifts. And so we see in very broad strokes the rough colors, and our brains are actually filling in the rest of the colors. This is a very powerful tool. Because, and here's an example from Wikipedia of a YUV image. Here, they've split out the color data into two separate planes, which is the same as before. It's just a different way of doing it. So we have the color image in the upper left, the luminance image in the bottom, and the color data on the right. You can actually store a fraction of the color data and cut the total size of the image in half. So a lot of the savings you see, for instance, in JPEGs, yes, they do cool stuff around frequency domains and wavelets, but if you were to encode a JPEG on iOS and you choose 99% image quality, but then go up to 100%, you'll see the image size doubles. And that's because then iOS is storing the full color data. Very often in image compression, a key savings is to just throw out or to downsample the color data because your eyes can't perceive the difference. Cool. Now, the good news, or somewhat good news, is it isn't difficult to reassemble the RGB data if you have YUV. It only takes one shader that does a matrix multiplication to mash it back together. What's weird is that it's so difficult to find that matrix. And of all places, Apple finally gave you some copy and pasted shader code to do it in the ARKit code samples. And that's because ARKit, it will let you operate on the frames that are coming in through the system if you want to build your own renderer, but it delivers it as YUV. And there's a little snippet in the documentation that says copy and paste the shader to get yourself some RGB. Why does ARKit do YUV? Why does the system use YUV? Well, it goes back to performance. If you're shuffling around half the amount of data, that gives you more bandwidth to be shuffling around other important content. Cool. So great, we've got a color image, but it's dark. Why is it so dark? Okay. All right. Here's another fun optical illusion. If you ask me to create a linear gradient like this on screen, this looks fairly linear. I think the screen it's a little darker, but I have a link to the gradient in another slide if you want to check it out on your laptop. But if you were to look at a linear gradient, you'd probably think that the middle value is like 50% of the color value, or in this case, 128. Okay? That's not actually the value that's being stored in a buffer somewhere. In fact, if you were to draw a gradient by just writing a loop that goes from 0 to 255, you would end up with a gradient on top. The linearly perceptive one on the bottom, the one that your eyes like, that middle value is way on the right side. And this is because our eyes are more sensitive to shifts in shadows than in highlights. So this has an important implication, and you definitely can't see it on the projector here. But if you were to encode your data linearly, just where the shadows have the lowest values and the brightest ones have the brightest, you'd see very ugly banding in the shadows because there just aren't enough bits to store the useful information that your eyes are perceptive to. So that brings us to one of the most difficult challenges in beginning programming for graphics, which is the idea of gamma. This is really, really, really important. What we do to get around this lack of bits is that when you capture an image, before it's stored on disk or in a buffer somewhere, it applies a transform function right there to boost it so that it looks a little brighter, but there's more bits to work with in the shadows. Later, when it's time to display your image on screen, your monitor applies the inverse of the function to make it look a little better. So it looked more like the original image from earlier. So you want to be doing operations in that linear display curve. Okay, so what will end up happening is a lot of people will not be thinking about this. They'll only be thinking about the values that are coming off of their monitor. So if you have two images and you need to merge them together, and you're assuming that they're linear, where one image is image A plus image B divided by 2, your math is totally off. And it's the most painful source of graphics bugs you can imagine. Tons of systems have issues with font anti-aliasing because people render fonts assuming that it's a linear color. So what that means just that when we actually go to display the image on screen, make sure that you're outputting a gamma curve so that your monitor can actually make it a little darker and things look correct later. So everything looks good as far as color. Everything looks the appropriate brightness value. The last problem that we're going to run into is we go to display it on screen, and you can't see it too well on the projector, but the colors here are a little off. Like this is a little more pink, and this looks like the appropriate red that we saw in real life. So what is going on there? And this is a problem that has occurred only in the last few years as we're now dealing with devices, I think, from iPhone 7 and above. Color spaces. It's the Y2K bug of graphics, where everyone made assumptions about what color space you're working in. So what is a color space? This horseshoe represents all of the visible spectrum that your eyes can see, unless you're a genetic anomaly or you're a dog. The problem is that this triangle in the middle is everything that most monitors can display, the sRGB color space. Okay, it's a very small subset, so if there's a value in the real worlds that you can't display there, you need to perform some math to squeeze it into that tiny triangle. And then Apple ruined everything by giving us devices that could display more colors. And now, if you aren't careful and you don't know the color space you're working in, you could be rendering something that you think it actually belongs here, but it was sourced up here, and everything is shifted in the wrong directions. The good news is, as long as you're aware of color spaces, it's just another matrix multiplication to move things into the right spot. The bad news is, you need to be aware when you're setting up your camera what color space you've requested from the system. In fact, some of the presets will give you wide color, and what you'll actually be displaying on screen may not be set up properly to display the wide color, and then everything's shifted in the wrong direction. Cool. And if you can get through that last hurdle, you now have a very simple video renderer. So just to summarize everything we've covered, we talked a little bit about the render loop. So that's the core loop that you need to keep fast. We talked about shaders, vertex, fragment, and compute shaders. The most important lesson about performance is that you want to focus on data, the amount of data, and the transformations you're making on data. And finally, we talked a little bit about the graphics theory, converting from YUV to RGB, paying attention to gamma, and then making sure you get the color space correct. And there you go. You have everything you need. Awesome. So does anyone have any questions?